Now, in the Lorentz transformation, you will have to keep in mind some history, that how these things were derived. There were many physicists were just deriving or sorting out this issue, and it was in 1887 the student of Maxwell, Oliver Heaviside, he just said that when you are having a spherical charge distribution, like spherical charge, you consider a spherical symmetry around it. And for the first time, he found that when the charge is in motion, the spherical symmetry remains no more valid. Like its symmetry doesn't remain spherical in nature. And that was the turning point, that he said that a spherical symmetry is seized, it changes, it ceased to exist. And that was the turning point. While this was by, let me write the name, Oliver Heaviside. But another person, the very famous one, the Fitzgerald, said that maybe the distortion that the Heaviside has observed, like the distortion in the spherical geometry doesn't remain spherical anymore when the charge is in motion. That distortion may be due to some intermolecular forces. So he just commented on that one, that it may be due to some intermolecular forces. But Fitzgerald was the one who himself was explaining this situation, and it was the this person and Larmor, these Fitzgerald, Larmor, they were in favor of the ether theory. The theory which was proposed by Boyles, they were in favor of that yes, this ether exists, this luminoferrous medium does exist. And they were in favor of it. And this way they were explaining this situation. So Fitzgerald was the first person who just gave hint for the length contraction. Means it wasn't something else, but over there he found that length is being contracted. And it was the Larmor who for the first time indicated time dilation. Right? Length contraction from Fitzgerald, time dilation by Larmor. But if we look at the Lorentz derivation, so Lorentz worked completely independently, and he derived this set of, you can say, result from his different calculations. But Larmor died in 1900, while Lorentz died in 1904, and just at the end of that year, means just in 1905, it was spring 1905, that Einstein derived the set of Lorentz equation in a completely different way. And he was the one who was not in favor of the ether theory. He rejected it. And by keeping the Galilean laws, the laws of physics remains the same, and an inertial frame of reference, he said that the speed of light is constant. It doesn't need any reference. It doesn't need any existence of ether. Right? So as we covered Galilean and the Lorentz transformation, in the Galilean transformation, we said that the space coordinates are relative while the time is independent of the motion of observer or source. Time is something universal. It will not change. And that caused some issues with our calculations because the position was different in two different frames. Velocities were different, but the acceleration came out to be the same. And when we further did our calculations, then we came to know that there is an issue with the time as well. The time seems relative to. And for that we started from the Lorentz transformation. We derived that factor, which the factor was telling or making the two frames to measure the same thing. And that was the success of the Lorentz transformation. So the basic differences between the Galilean transformation and the Lorentz transformation are that Galilean transformation is valid when V is very, very less than C. But Lorentz transformation is less for V very, very less than C or V comparable to C as well. And another thing, when V is exactly equal to C, then the Lorentz transformation becomes invalid, means the equations are not valid then. So this is one of the difference between this one. And according to the Galilean transformation, T was an absolute thing. It was not relative. While in T was equal to T prime, while in Lorentz transformation is not equal to T prime. The time is relative as well. Just as here, x prime was not equal to x. Here, not only x prime is not equal to x, but t prime is also not equal to t prime. The Lorentz transformation. So the Lorentz transformation is much broad because it is covering a big range of velocities. It is valid for the Newtonian mechanics as well, or Galilean mechanics as well as for the modern explanation of the theory of relativity as well. Now from the Lorentz transformation, we also concluded that the moving frame clock will run slow. Like for example, we are having a frame and this frame is such that it's like a clock. That light goes here and then back here. And let's say this is having its length equal to 1 meter. Then we know that the speed of light is 3 into 10 power 8 meter per second. So this one oscillation, it will complete. It is 2 meter then. Because 1 meter up and 1 meter down. So it means in 1.5 into 10 power 8 oscillations will be completed by light in 1 second. Because you divide this by 2 meter, then 1.5 10 power 8 oscillations the light will do. Clear? In 1 second. But now let's see that the same frame just goes with a speed which is closer to the speed of light, means this was observed by the observer here. Now the same, it is going up and then down, but now this is a space shuttle, for example, which is running at a speed very close to C. Now how the light will behave here? It will go up like this now. It will just, you can say, start from here, and then it will be, this one is also going comparable to the speed of light. So it will seem that the light, that this observer will observe that the light is starting like this one and touching here. And then that light is back here. So it is that frame on which it is back. Right? Now this observer sees that the time has dilated, the time has been extended, like the oscillation has been covered. One oscillation has been completed in a long time. So this is time dilation. Or we say that to a stationary observer, the moving frame clock is running slower, while the same will be observed for the other frame as well. Because each of the frame considers itself stationary while the other is moving. So we can finally say that the moving frame clock will run slower. Now let's see if both S and S prime are measuring the velocity of a moving particle. So we consider a frame which is S. This is frame S, and here is a particle which is moving with speed v, and it is according to this frame, this v is equal to x over t. While another frame which is moving with some speed, this is S prime, let's say this is moving with speed u, and this will measure the velocity, let's say w, the velocity, I will write like this. W is the velocity of the particle which this one measured is x prime over t prime, right? This is a particle, this is a body which is moving with speed v, and both the frames are measuring its speed. So this one measured x over t is v, and this frame is itself moving at a speed u, and this measure, the speed of it is x prime over t prime, our earlier notation. Now I can write that w is equal to x prime over t prime, and now put the values. What was the value of x prime? It was gamma x minus vt, in this case it is ut, because the frame is moving with speed u, and divided by, what was the time? Time t prime was gamma t minus u over c square, and x times gamma. This was the t prime value that we derived from the Lorentz transformation. Gamma will cancel with gamma, and we will have minus ut divided by t minus u over c square x. And now we derived by t. So divide this by t and this by t. Mathematically this is not a problem. So x over t minus u divided by 1 minus u over c square and x over t. So for x over t I can write v. X over t I can write v. And now I can further simplify this one. So x over t is v minus u divided by 1 minus u v over c square. Clear? This comes out to be the velocity of the body or of the particle which the moving frame has measured. And similarly, the velocity which the frame has measured will come out to be, you can do the same calculations, and it will be w plus u divided by 1 plus u w divided by c square. With the same tactics, you write their equations and then do simplify. You will get that v is equal to w plus u. Now, if for example, these two, we know that they are different, right? W is, let me write this one here. This is equal to w, and this is equal to is w plus u by 1 plus u w over c square. Now this velocity, the velocity measured by the moving frame is different from the velocity measured by the stationary frame. Both are different. But now let's say this body is moving with the speed of light, and they are now measuring their speed. So what is actually the situation now? We say that W is equal to C, right? For W equal to C. W is the velocity of the body which the moving frame is measured. And now this measure it to be C. So we will put now in this equation, and let's see that then V is equal to W plus U 1 plus W over C square. Now when W is equal to C, put the value, then this is C plus U divided by 1 plus UC over C squared. One C will simplify with this, and we will get C plus U divided by 1 plus U over C. And this will C plus U, and this will become C plus U over C. By taking C as the LCM, we simplify. So C plus U, and this one, if it moves up, then it becomes C over C plus U. And C plus U cancels with C plus U. And this comes out to be C. Right? V comes out to be C as well. What we assumed? We assumed, you know that V and W were different. Okay? V and W were different. Like V is the velocity measured by the stationary frame. W is the velocity of the body measured by the moving frame. both were different. But when we said that, let's say the moving frame measure that velocity AC, although it is moving with speed u, but measure that speed AC, and we put in the equation, this is the velocity which is measured, which is the velocity of the body, right, which is measured by the stationary frame. And the stationary frames also measure it equal to C. And here is the agreement, and here is the success of the Lorentz transformation. That when you put the Lorentz transformation, when you put the Lorentz equation here, then they, both the moving and the rest frame will agree on one speed. And that one speed will be the speed of light. Similarly, if W is, means I take this equation, W equals U V minus U1 minus UV over C squared. And now if I say that V measured by the stationary frame is equal to C, then what the moving frame will measure it? Like the body is moving now with speed of light. Then put the values. V is equal to C. C minus U. 1 minus UC over C squared. C minus U. And this is 1 minus U over C. So it is C minus U. C minus U over C. Cancellations. And then this thing also comes out to be C. So the speed of light is a speed which is independent of the motion of the frame, which is independent of the motion of the observer or the source. And this was the finding of Michelson and Morley. They said no ether is there. Although Lorentz himself was in favor of the ether, he wasn't against it, but from his equation, this thing proves that when it comes to the speed of light, every observer, every frame will measure it equal to C. And that is all about the Lorentz transformation. Yet we have to explore more things in it. Like we will have to now consider in the forthcoming lecture that whether the Maxwell equations are invariant under Galilean transformation, because in the Maxwell equation you also have the space and time relation. So whether they are invariant under the Galilean transformation, are invariant under the Lorentz transformation, or when we apply these transformations, then things become different. So we will discuss that one as well. In the Lorentz transformation, we will also discuss the, here we only agreed on the speed. Like C is equal to space over time. We agreed on speed, but we have not yet agreed on space. We have not yet agreed on time. Because we know that in the Lorentz transformation even, the space measured by one frame is not the same as measured by the other frame, while the time measured by one frame is not the same as by the other frame. So then we should go to that space and that time as well, which we call the standard length and the standard time. And that will also be the same for whether a frame is moving or a frame is stationary. So we will go to the standard length and time as well as we move or we concluded about the standard speed. This is the standard speed. These two are relative. we will find their standards, individual standards as well. Then whatever frame will be measuring the space, it will be the same for both the frames. Stationary are moving with this speed or more speed. It will not matter. And similarly, the time as well. So, thank you.